Alright, welcome back everybody. In this video we're going to continue with the finding intervals of convergence lesson and look at examples 3 through 5. So we're going to start here by using the ratio test to get our base interval of convergence for this series. So we've got the limit as n goes to infinity of n plus 1 factorial times 2x plus 1 to the n plus 1 all over n factorial times 2x plus 1 to the n. And let's see, simplifying this, we end up with the limit as n goes to infinity of the quantity n plus 1 times 2x plus 1. And in order for this to converge, that needs to be less than 1. Now, we've got a little bit of a problem here in that as n approaches infinity, this n plus 1 inside the absolute value, that also approaches infinity. And so this is going to be one of those situations where the only way that what's inside of here can be equal or can be less than 1 is if in fact it's equal to 0. And the only way that can happen is if this quantity 2x plus 1 is equal to 0. That's the only way we can get what's inside here to be less than 1. And so we solve this and we find that x is equal to negative 1/2, which is the center of this series. And in fact, that is the entire interval of convergence is x equals negative 1/2. So it converges absolutely on the interior of that, and it converges conditionally nowhere. Alright, example 4. We're going to set up our ratio test to find the base interval of convergence. We take the limit as n goes to infinity of quantity 10x to the n plus 1 over n plus 1 factorial times the reciprocal of a sub n. And simplifying this, we get the limit as n goes to infinity of 10x over n plus 1. We need this to be less than 1. Now, since the denominator is going to infinity, that means no matter what value of x we put in there, this is going to approach 0, and 0 is always less than 1, and therefore our interval of convergence is going to be all real numbers. And then it converges absolutely everywhere in the interior of that interval. And it converges conditionally nowhere. Alright, so the fact that n is going to infinity here makes this series converge no matter what real number value of x we choose. Alright, so those last two are kind of quirky examples here. Let's look at the last one, find the interval of convergence of this series, then determine. So again, we're going to set up our ratio test. The limit as n goes to infinity of the absolute value of, scroll back up here a little bit, give myself a little bit more of an easy reach. When we put n plus 1 in there, it becomes x to the 2n plus 2 times the reciprocal of a sub n. And simplifying all of this, this becomes let's see, x to the second over negative 3. And in order for this to converge, that has to be less than 1. Absolute value of that has to be less than 1. So we've got -1 is less than x squared over -3, which is less than 1. Multiply both sides by -3, or all three parts by -3. Now this restriction right here is redundant. We know that x squared is positive, and so to say that x squared is greater than -3 is really not giving us any extra information. So in fact, we know that x squared has to be less than 3, and taking the square root of both sides, we end up with -3. Root 3 is less than x is less than root 3. So that's going to be our base interval of convergence. Now we need to test this at the endpoints. All right. So at x equals negative square root of 3, and at x equals positive square root of 3. So if we put negative square root of 3 in there, the x to the 2n, this becomes 3 to the n power. So we've got 3 to the n power over -3 to the n power, and this turns into the sum from 1 to infinity of -1 to the n. And the same thing happens at x equals square root 3. This becomes the sum from 1 to infinity of -1 to the n. Both of these diverge because of the nth term test. That diverges and that diverges, and so those endpoints are not included. So our interval of convergence is going to be the same. And for part A, where does it converge? Absolutely everywhere in the interior of this. And where does it converge conditionally? Nowhere. Okay? And so one of the biggest things for you to work with here is just do a bunch of examples of this and make sure you continue to, remember that we need to test out what happens at the endpoints. Sometimes we'll find that those endpoints converge. A lot of the examples that we looked at in these videos have divergence at the endpoints, but you're going to see convergence at the endpoints at least a fair amount of the time. So keep your eyes open for that. Anyway, that's the end of this video, the end of this lesson, and in fact, the end of this unit. So see you guys next time when we come back for the last unit of AP Calculus BC. Have a great day.